Day 46, page 975, problem 35. The classic Michelson interferometer, which I have pictured on the left here, overhead diagram, which is the same technology that they've used for the LIGO's detectors for gravitation waves that you maybe heard announced in last spring sometime. We have two of these detectors. If you're looking at the picture in the upper right, I don't know if that one's the one from Washington, the state of Washington, or the one from Louisiana, but the setup is much bigger. It's like 4 kilometers, 2.5 miles on each of the two perpendicular arms. In the Michelson interferometer, the actual one that he used, it's lab size. It's probably no more than a meter by a meter. But you start off with a beam of light that comes in, goes through a beam-splitting mirror, and then hits two other mirrors, bounces back, and get an interference pattern on the screen. So we have this interference pattern down here, which is alternating circles if you start with a laser dot. Right now, basically showing on this particular screen, it looks like dead center on that screen there is there's concentric circles, but in the dead center there's kind of like a white dot, barely visible. I don't know if I can, but you can see it there. That's basically destructive interference, where the beams are canceling out when they come back together on that screen. And then the dark concentric circles you see in that picture right there would represent constructive interference. But as you move a mirror, so for example, this mirror right here, let's say this mirror right here is movable. You can move it in or out. Bottom line is, whenever you move that mirror, if you move the mirror 1/2 wavelength, 1/2 lambda, basically you've effectively changed the path length for that particular beam. In this case, they've got it highlighted in green. It's not necessarily green light, but if you move that mirror inward or outward 1/2 wavelength, you change the path length of that beam, of that arm, by 1 full wavelength, because you've shortened it going out and coming back. So every 1/2 wavelength shift in that mirror changes the pattern back to what it looks like in this picture over here in the bottom right. So you go through what's called a fringe pair. So the pattern will kind of look like it's moving in or out, but then it'll come back to this particular same exact pattern by each 1/2 wavelength move. So now it says in the problem here, you've gone through 92 fringe pairs. In other words, if you go through 92 fringe pairs, that means you've moved the mirror 92 1/2 wavelengths. Well, 92 1/2 wavelengths, 92 times that many 1/2 wavelengths, gets you 46 full wavelengths. In other words, they've moved that mirror 46 wavelengths, which matches up to, it says 2.53 times 10 to the negative fifth meters. So in other words, we have 46 times lambda, 46 wavelengths, equals 2.53 times 10 to the negative fifth meters. So solve that for lambda. So lambda is just going to be that 2.53 times 10 to the negative fifth divided by the 46. That will give you the wavelength of the beam that was used in that particular situation. So just to summarize again, this particular interferometer didn't show them anything about the luminiferous ether. In other words, they basically proved that there is none, contrary to what they thought. But it's a useful device, the interferometer, in detecting gravitational waves, which we needed a much more sensitive device. That's why the arms are much bigger, to see an interference pattern on a particular screen. Obviously, it's a little bit more technical than this diagram shows, but the basic premise is there. You get this interference pattern that's shifted by the gravitational waves as they pass through the different directions of the two different perpendicular arms of that detector. Also, just quick note, LIGO stands for Laser Interferometer Gravitational Wave Observatory. I guess the W wouldn't look too good in there, so LIGO sounds pretty cool.